Hi, my name is Manish Gupta, and in this video, I'm going to talk about Attention XML, which is basically about using which is a method for label tree-based attention-aware deep learning model for high-performance extreme classification. Right? If you have not watched the Parable video before, this is a good time to actually watch the Parable video and then come to this one. Okay. So what is attention XML? Well, in short, it is basically a deep learning based method, which is also related to label trees for extreme classification problems. What are extreme classification problems? Well, problems where you have input data point, and you want to classify it into a few of several labels, right? So this label set is very huge, and that is why it is called extreme classification. And you want to classify this point into a subset of those labels. Specifically in this paper, people deal with extreme text classification, and there are so many applications for extreme text classification, multi-label text classification also, like item categorization, web page tagging, news annotation, and so on. So attention XML essentially is a combination of deep learning and label tree based parable method for extreme classification. Um, Essentially, it has these three things which I'll talk about in the next 2 or 3 slides. Right? Shallow and wide tree compared to the parable method. So remember, in parable, they proposed to create a tree with just the left and the right child, just 2 children per node. But attention XML sort of believes that if you have just 2 children per node, you can end up with very tall trees, and that can lead to a lower performance. And therefore, they believe in shallow and wide trees, shallow and wide probabilistic label trees. So they're called as probabilistic label trees because, well, you partition the tree based on in the label space, and also, whether to take the left child or the right child or both is decided based on probabilities of visiting that node based on the training data, right? So that is why it's called probabilistic label tree. And attention XML sort of believes in shallow and wide probabilistic label trees. We'll call them as TH. And rather than just two-way shallow XML, attention XML basically is K-ways. Okay. Now, in Parallel, for each of those internal node classifiers and leaf node classifiers, it basically used one versus all classifiers, sort of trained in a logistic regression manner, right? So in Attention XML, this is what is exactly very different. So they basically use BiLSTMs, bidirectional long short-term memory networks for internal as well as leaf node classifiers. And they also have an attention layer, which is what basically gives it the name Attention XML. So it has multi-label attention, and this multi-label attention not just gives you good accuracy overall on the entire data sets, but is particularly helpful for tail labels. Okay. So that's a brief about what is attention XML. Now, in this slide, in the remaining part of this slide, I'm going to talk about how is this probabilistic label tree constructed in attention XML. Okay. So to construct that probabilistic label tree, as you see in Attention XML, you do a few things. But let me first talk about basic things, right? So essentially, as you see, there are 4 labels in this tree, right? So essentially, they call it h equal to 2 because h is the height of the tree. And, in the height, they do not count the root node and the leaf node. So therefore, h is basically just 2. Okay. Also, you see L equal to 24. So this tree has been drawn for 24 labels. Of course, labels form the leaves. So since there are like 24 leaves, I'll basically call it 24 labels. Okay. K equal to M equal to 4. So essentially what you see here is that, each of those nodes essentially have 4 children. Each of those nodes have 4 children, except for the root node, right? Each of those have 4 children. Therefore, what you have is k equal to 4. So it's a 4-way tree in that sense, right? And also, if you basically look at the last node that was not split, it has less than equal to 4 nodes. That is why m equal to 4. So that's basically, attention XML. Or rather, that's basically the broad understanding of the tree, right? Now, given a particular data point, let's say it has 4 labels, label 1, label 2, label 3, and label 4. In that case, all the nodes which are on the path to those labels right from the root node, you basically call their Zn parameter as 1. So which is what is marked as positive here. And everything else, those subtrees which are not taken or those nodes which are not taken, they're labeled as negative, Zn equal to 0. Okay, so that's the basics of understanding this tree. Now, the way this tree is created in attention XML, it's of course a k-way tree, as you can see, right? The way it is created is to basically start from the parabol tree. So you start from the parabol tree, call it T0, right? And you're going to create the attention XML tree TH using this algorithm which is mentioned here. And I'll go over that algorithm step by step. Okay. Of course, you have training data. So you have training data in terms of X, the training data point, and Y, which is basically the set of labels associated with the training data. You also have K, which is basically 2 raised to C, so which is the number of ways in the multi-way tree that you want to create in attention XML. And you have H, which is basically the height of the tree that you expect to create in attention XML. Okay. So the way you do is to start with your T0. So you basically have, a very drilled down tree, and it's basically a two-way tree. So that's basically that. And, you see, you have like 24 nodes. So I've just drawn here 8 of them, but you'll have like 24. So you have the next level as well and so on. Okay. So you have that. Now, what you do is to start by saying S0 is the parent nodes of the leaves. So you don't really care about the leaves. You basically consider the S0 as the first level. And what you want to do is to merge a few nodes in few of those internal nodes so as to essentially reduce the height of the tree and make it wider. Okay, so that is what you would do. So for example, let's say if this is my S0, I could basically consider this as my S0 given this kind of a tree. Okay. So what you do is to essentially then for h equal to 1 to h, so you're going to repeat this process h times, right? So whatever is the final height that you desire, okay? For h less than h, you're basically going to say sh, in our case, let's say in the first pass, it's s1. It's going to be seeth ancestor node n of nodes in sh minus 1, okay? So essentially, let's say if I basically want to have c equal to 2, c equal to 2 would give me like a four-way tree, right? So if I want to have c equal to 2, what I would do is to basically consider seeth ancestor of node n of nodes in sh minus 1. So if this was level S0, right? Maybe, to make it more fun, let me call this level as S0 and imagine that there is a level of leaves below it. Okay, so this is S0. And if I fix C as 2, what I'm going to do is to basically just look at this entire subtree and I just merge it into one node, Okay. So basically, I'm going to basically now have, 4 children directly. So 4 children directly. So that's that. So so sh is essentially the seeth ancestor node of nodes in sh minus 1. And then what I'm going to do, I'm basically going to have th as th minus 1. So whatever is the tree, T1, so tree T1 will be same as tree T0 there. And then this is the merge operation which is going on. So remember, you essentially have for all the nodes in SH. Remember, what are the nodes in SH? Well, the nodes in SH are at 2 levels right up. Okay, seeth ancestor nodes, that's SH. Okay. For all nodes n dash, which are in SH minus 1, for all those nodes at that level, and node n is the ancestor of n dash. So if node n is the ancestor of n dash here, right? You basically say that, hey, n becomes the parent of n dash. You directly connect n to n dash. Basically resulting into a multi-way tree of that kind. Okay, so that's that. And then you keep doing this at multiple levels, so that until the height that you desire, until the final height that you desire. Okay. So that's how a multi-way, a wide tree and that to a shallow tree is actually generated or created, given. Next, let me talk about how is this attention XML model trained, right? So we have the probabilistic label tree already created. Now we need to know how is this, how do BiLSTMs fit in and so on. Okay. So you train one LSTM. So remember, in Parabel, we used to have these internal and leaf node classifiers. That is the same thing that you want to train in Attention XML as well. So you are going to train one BiLSTM per level in a top-down manner. So you basically start by saying that, hey, I have the first level. I want to create a BiLSTM which tries to predict the nodes at that level, or which tries to use the nodes at that level as labels. Okay, and then you try to create another LSTM, train another LSTM for the second level, train yet another LSTM for the third level, and so on. So if your tree has like h different levels, then you're going to have h different bi-LSTMs in that senses. Okay. So you train one LSTM per level in a top-down manner, attention XML1 to attention XML H plus 1. Well, you have H plus 1 because H is essentially ignoring the last level, which is basically the leaf nodes themselves. Okay. So each level of PLT, each level of this tree is an XML problem. So you treat each level as an extreme classification problem where you have to classify amongst the set of the children or the nodes at that level, the nodes at that level. Okay. So now how do you train this attention XML at any level D, right? So at depth D. So the way you do this is to basically consider, first of all, what are going to be your active labels? Okay. So if you look at any level, so essentially if I have a tree, let's say a four-way tree, so that's that. And if I'm considering this particular level, if I'm considering this particular level, well, I have these 16 things at this level, right? But I may not want to basically learn in the space of 16 things for each example. Because if I do that, let's say if I have like 10 such levels, then at the 10th level, I may have just too many nodes. And then, the softmax may be a big problem. And therefore, the way they avoid this problem is to say that for any particular example, only a few of these levels are going to be active. Only a few of these nodes are going to be active. Okay. So for a particular sample X, you first want to figure out which of these nodes are going to be active. Of course, some of them are going to be positive, some of them are going to be negative, but which of them are going to be active is what you want to learn first. Okay. So for a particular sample X, you basically choose these nodes. And how do you choose these nodes? Well, you sort them. You first sort them by their Zn values. So you first sort them by their Zn values. So for this particular sample, training sample, if particular nodes were active, you of course want to keep them active in the sense that they were traversed, then you would surely want to keep them. But you also want to you also want to sort them by score of attention XML D minus one. Okay. So what do? You basically, if you have to choose at this particular node, you first choose the D minus one nodes. Sorry, yeah, this was a little unclear. So essentially, if you want to choose the nodes for labels at the level D, right, you actually first make a choice at D minus one. And how do you make that choice? Well, you basically descending order sort those nodes. And the way you would sort them is by looking at active nodes, by nodes which are traversed first. So where Zn equal to 1. So you first keep those nodes. And then you sort them further at the second level using scores predicted by attention XML D minus 1. So for this particular example, attention XML D minus 1 is already trained. So you ask it for the scores. And the most promising ones is what you keep. So you keep the top C nodes at D minus 1 level and then choose their children. So let's say if I selected this node and this node, then I'm going to take these four, and that's my G of X, or that's my label set that is going to be active. Remember, this is not all positive labels for the particular sample X, but this basically indicates promising labels, those labels which are positives or hard negatives, right? So in that sense, it also helps you do this hard negative sampling rather than only using nodes which are positive, nodes with positive parents. Okay. So that's how you essentially decide the nodes for which you are going to consider the loss, for which you are going to backpropagate the loss when you are going to train attention XML at level D. Okay. So the way that now the way the prediction is done is just like parable. So you essentially do beam search and you essentially train three PLT, an ensemble of three probabilistic label trees. So essentially you have three trees and you sort of do ensembling on top of them, and also you do beam search starting from the root node at prediction time. Okay. Now, each of those bi-LSTMs that we talked about is bidirectional in nature. It's trained using the features as 300-dimensional globe embeddings of your input document or input data point. Okay, so the features that it uses, the embedding that it uses is 300-dimensional globe embedding. It uses the binary cross entropy loss, just like Parable. Multi-level attention. By the way, yeah, the bi-LSTM that we didn't discuss, the details are as follows. The attention part, right? The details are as follows. So it's a typical attentional bi-LSTM, and now attention-based bi-LSTMs are very popular these days anyway, so it's not like a big deal. But in 2019, it was relatively still popular, relatively still new in that senses. Okay, so at the base layer, you have this word representation layer, which is glove layer, and then you have these bi-LSTM layers, and then you compute attention values, these alphas. The way these alphas are computed is using similarity with respect to a learnable weight vector, so W. So it's a learnable weight vector W. You randomly initialize it and train it over time. You train it by using the same vector across several examples in the entire training set. But remember, there is a weight vector per label. Now, this is interesting. Rather than so typically in self-attention, people keep only one weight vector, but here they actually here they have proposed to keep one weight vector per label. Okay. So that's basically what defines those weight vectors. They're learnable weight vectors. That gives you, applying softmax on top of that gives you alphas, which are the softmax weights. And then you use those softmax weights so as to essentially get a representation M, which is basically fed to a hidden layer and then to the output softmax output layer, which is sigmoid activation. And then you use it to compute the binary cross entropy loss. Now, of course, how many outputs you would have? You would have L outputs, where L depends on the on the size at a particular level. At the last level, of course, L is the actual L, the actual set of labels in your entire training data set. Okay. So the other interesting part that they do is that they share these weights across all labels. So same parameter values are used for all labels at the fully connected and the output layers. So all of these labels essentially have the same parameter values, and sharing these parameter values, of course, makes computations efficient and saves the space. So the model becomes much smaller in size. The way these parameters of attention XML, so the parameters in the BiLSTM and the parameters in the output layers, the way these parameters are initialized is using attention XML D-1. So use the attention XML of the previous level so as to initialize the parameters, the learnable weights, in the next layer, except for the attention layer. So except for these attention layers, the weights that you train, of course, those weights are trained per layer separately. You don't initialize them from the previous layer, but all other weights in the BiLSTM are initialized from the previous level. So now that said, how does attention XML perform? Well, it performs better than several other methods. So here you see results comparing attention XML using 8 different methods. There is attention XML1. Attention XML1 is basically using only one probabilistic label tree, not like an ensemble of 3, while attention XML uses an ensemble of 3. Right? You see results on 3 different data sets, on 6 different data sets, Urlex, Amazon 670K, Wiki 10, Wiki 500, Wiki 1031K, 500K, Amazon categorization 13K, and Amazon 3 million. Okay. And you see results on these 3 metrics, precision at 1, precision at 3, precision at 5. Right? And you observe that attention XML sort of outperforms each of those methods. In fact, attention XML1 also outperforms most of the times. So all of those methods in most of the cases, which basically means that there's no need to really keep an ensemble of 3 unless you really want very good accuracies. Even with one probabilistic label tree, attention XML is able to beat all of those existing state-of-the-art methods in 2019. Now, how does it perform on tail? So therefore, to do this testing on tail, these folks reported PSP metrics. So recall from the previous videos that PSP propensity scored precision kind of metrics are really good metrics. They give weightage, high weightage to the tail, and that is how they specifically zoom in into the tail and tell you how the XC classifier is working on the tail. And what you observe here is that attention XML is comparatively way better than Parabel across different data sets, and also on these 3 different metrics. Okay. Specifically, you can also look at the attention values for more interpretation. So specifically in the paper, they actually show the visualization for the attention as well for categorization of this Wikipedia page. The Wikipedia page title is Gmail driver. And of course, Gmail is a very reasonable label to provide to this Wikipedia page. And what to observe is that attention XML, of course, guesses the label correctly while paying a lot of attention to keywords like Gmail, email, and attachments on the entire, on the words mentioned on the entire web page. Okay. So in summary, in this video, I talked about attention XML, which is a label tree-based deep learning model for extreme multi-label text classification. It has 2 main components, a multi-label attention mechanism with raw text as input, which allows you to capture the most relevant part of the text, which is relevant to this label. Okay. So remember, this attention that is provided is specific to the label. So you essentially try to figure out which part of the text is most relevant to the label. Okay. It also uses a shallow and wide probabilistic label tree rather than Parabel, which basically proposes a binary and a deep tree. Right. So this shallow and wide tree allows you to handle millions of labels, especially for the tail labels. And comparing to 8 different strong baseline methods, they showed that AttentionXML sort of performs better over 6 different benchmark datasets. Okay, that's it for this video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage.